All right, here we are. We're on number 17. Awesome. If you're on 17 but you haven't really figured out 16 yet, you're probably wasting your time. Make sure you're really good at 16 before you come here. This one's our tough one here. So we have Javi bouncing on a trampoline. And when he leaves the trampoline, he ends up spending 1.5 seconds in the air, which means it's 0.75 seconds on the way up and 0.75 seconds on the way back down when he's in the air. On the other hand, after he touches the trampoline, he's on the trampoline for less time. And if you've been on a trampoline, you've felt that when you bounce on the trampoline. You're on the trampoline less time than you are on the air. And the fact is, I've just decided to make that trampoline time 0.75 seconds. Okay? When he's in the air, that 1.5 seconds, we can say that half of the time is on the way up and half of the time is on the way down. So that we can take our time here to be 0.75 seconds. Okay? And we do that so that the initial velocity that we'd like to know is unknown, but our final velocity is now 0, and that's going to enable us to be able to do the problem. I've decided to have us use g as negative 9.8, and so let's take a look. So acceleration is negative 9.8. We have the final velocity is 0. The time on the way up is 0.75. I'm asking about the initial velocity here, so that enables me to go ahead and just plug into this equation. Vf equals Vi plus At. Don't forget your negative on the 9.8. Right? When we solve for VI, we end up getting 7.35 meters per second. That's nice because now that I know VI, I can now just solve for delta x simply using this equation. We could have used another equation instead, but in any case, now I can just plug in here. Again, I'm getting sloppy with the units, but that's because I have my units nicely stated here or here. In any case, plug in the numbers here, making sure to remember my negative on the 9.8 because the acceleration is downward even though the object is moving upward. And this gets us a 2.76 for our displacement going upward. So we have our final velocity on the way back down, also known here because we know the velocity at the beginning on the way up is going to be the same as our final velocity on the way back down. And if you don't believe me, you can go ahead and redo this problem with VI being at the top as a 0 and see what you get for the final velocity on the bottom. You'll get a negative 7.35 for our final velocity on our way down. So we've pretty much solved what's happening on in the air. So let's take a look at on the trampoline. So on the trampoline, we have this is our initial when we're touching the trampoline for the first time. Notice our velocity is negative, right? Our velocity is negative because we're on our way down and we've just touched the trampoline. So our velocity is negative. What's interesting here is that the acceleration has to be positive. It's going up. And that's because we sense the trampoline is pushing us upwards. Our net force is upwards. So we know that the acceleration is also upwards. And we don't know it. So here we're going to put question marks on our acceleration. In any case, we can't use negative 10 because it's not in free fall. So we've got our initial velocity when it touches the trampoline is actually known to us. Because back here when we figured out this 7.5 initially upward, that's also the 7.5 final as we touch the trampoline on the way back down. So that gives us this negative 7.35 meters per second as our initial velocity going downwards when we first touch the trampoline. Now the trampoline stretches downwards, and at its most stretched out moment, our velocity goes to 0. We get turned around and thrown back up. Okay? And that acceleration we're assuming is constant also on the way back up. So that acceleration upward is also with our velocity upward on the way back up. But let's cut the problem in half so that our final velocity is 0 at the bottom. So that's where this 0 comes from. And I said we cut the problem in half, but our our time, on the trampoline is 0.75, which means that the time we need to use is half of that right here, 0.375. So again, we know three things. We can solve for what we don't know. This time we're solving for acceleration, which we don't do very often, but in any case, easy to do, and we end up getting 19.6 for our acceleration. It's positive, and that makes sense because it's pushing upwards. We can also get our displacement now that we know our acceleration. We know our initial velocity. Time, make sure you use half the time. Time squared, so we're putting 0.375 squared. And when you plug all this into your calculator, you should get a negative 1.38. And the negative makes sense because we're going down from the trampoline. Okay, let's take a look at the graphs. We've solved everything. Now it's just a matter of plugging things in. Here's our position. We had our 2.76 meters was as high as he went in the air. Here he touches the tramp. Notice for 0 here I've chosen the level of the top of the trampoline. And so this represents the trampoline being stretched downwards for our negative displacement. In any case, it goes down about negative 1.38. These are parabolas, so we have a parabola here, matches a parabola here, matches a parabola here, matches a parabola here. Very nice. Notice that when it's concave down, that's because our acceleration is negative, right? This is when we're in free fall. The acceleration is negative 9.8. Here, we're being pushed upward by the trampoline. Notice that our concavity is concave up, and that's because our acceleration, as we saw here, is positive. Okay. If we look at the velocity graph, it makes sense that this is while we're in the air. This whole time we're in the air. This is the moment that we leave the trampoline with our upward velocity. This is where we're as high as we ever get. Here we come back and we touch the trampoline. The trampoline is now pushing us upwards, and so our velocity slows down. We're still moving downwards. Notice this velocity is still negative. We're moving downwards, and this is the moment when the trampoline is as stretched as far as it is, and this is when we're as deep as we ever get. This part right here is why trampolines are always built up in the air, because they need to be able to stretch downwards. Otherwise, you'd slam into the ground, right? In any case, this is as far down as the trampoline ever goes, and this is when the velocity is 0 again. So velocity is negative here. We're moving downwards. It's stretched out. Now we're still on the trampoline at this point, but the trampoline is pushing us upwards, and this is the moment we leave the trampoline. Okay, and now it's just going to repeat. Here we are moving fast, upward direction, and now here we are slowed down. This is as high as we ever get again. Here we are with a negative velocity, so we're on our way back down, and then here we have our negative velocity, and we touch the trampoline again right here. And then again, we're still moving downwards, but the trampoline's slowing us down. And then this is, again, as deep as we ever get with the trampoline stretched out. And then the trampoline, at this point, is pushing us up again until our velocity is enough that we'd leave the trampoline. So for accelerations, here we are in free fall. This is us touching the trampoline. Here we are in free fall. This is us touching the trampoline with the trampoline pushing us up. Okay, this is a little bit idealized. In the real world, these lines wouldn't just jump like this. Our force would change gently. Accelerations due to a trampoline tend not to be constant. So it'd be a little more complicated, and we'd probably need some calculus to solve it. So let's just keep things simple with this approximation to what happens as you jump up and down on a trampoline. Anyway, that's a tough problem. You want to do this one probably twice. Just think through it, and wish you the best of luck. Make sure you see me if you're still not getting it, and see you in class.